All right. Hey, how's it going? Thanks for coming out. I'm Patrick. I do have to apologize for the way the slides are presented. The resolution on my screen is 4K, and this is like half a K. So it looks a little bigger on my screen than it does on there, so apologize. But anyways, I am Patrick. I'm here to talk about Python and software-defined radios. I work for a company called Ion Channel out of Frederick and Alexandria. It's a pretty good thing, and I am a nerd because I found out about these things like actually that they existed about 2 months ago, and I haven't stopped looking at them. So I'm here to actually talk about them. Hopefully nobody else knows more than I do, and I won't look like a complete idiot. But if you do, don't hesitate to speak up because I'm totally okay with you telling me that I'm wrong when I talk about something. So let's get into it. What is software-defined radio? Let me pass this around. This is what Matt sent out in the meetup. This is the SDR Smart New Electric $25 Amazon SDR that I found that works pretty awesome. You'll see in one of the other things that I show, it actually has, I think one of the more important things that it has is a very high sample rate. When you really start getting into that, you figure out like where you actually want to look at the signals and how to visualize them properly, and it's able to sample at this insanely high rate for a $25 thing. I was surprised. It was incredibly amazing. So what is software-defined radio? I pulled that description off of Wikipedia. It's a radio system, communication system where components that have traditionally been like pieces of hardware that people have built to do things to a radio signal. It's now all done in software. So a signal comes in, whereas you would have a traditional FM radio transceiver doing things like filtering or a low-pass filter and passing it to some sort of other thing that's doing some additional hardware modification of that signal. You actually do it all in software definitions now. So this is just a screenshot of a thing called GNU Radio, and it's a XML. You can't really see it on the screen, but it's a XML formatted. I think it's XML formatted document that is. This thing here is actually a high-pass filter. So it would be a component of the FM radio receiver, is this piece here. So each one of those that you see on the hardware diagram would be software-defined portions of that same diagram. But instead of being hardware pieces, they're actually software. So I found that to be fascinating that you can define the hardware components in software. Now it kind of reminds me of the thing that I really like about Amazon cloud type things, not to bring up Amazon, but that you can, not just in Amazon, but in the cloud now you can define your networks, you can define your components all via software. Everything's going to software, so that's kind of interesting. But SDR, software-defined radio, isn't new. One of the first things coined was a digital receiver back in 1970. So people were thinking about software-defined radios all the way back in 1970. A software radio was first coined in 1984, my birth year, so hooray. Also found out that there's a guy that was also born in 1984. Did anybody watch the Wild Wild Country thing on Netflix? Apparently that all happened around my birth year. It was really strange. Maybe that's why I'm so weird. It's okay. The speakeasy phrase, where the military started looking at using software-defined radios to do frequency key hopping between frequencies and encrypting radio communications, all via software from 2 megahertz all the way up to 2 gigahertz, was all around software-defined radio. So they were able to using that speakeasy phrase 1, and they also have phrase 2, which is still apparently in work, to be able to take ground forces and allow them to be able to communicate with the air forces and the naval forces and all the different things that existed. They were able to use a software-defined radio thing to get them to all be able to communicate in the same way. It's just fascinating to me that was, now in practice, coming from the military and having to deal with encrypted communications is an incredible pain in the ass. But in like training situations, it actually works out great. You could communicate with everything, unless you actually need to do anything with it. And then finally, GNU Radio, which It's funny, it actually started up around 2001. Free piece of software that you can use to define the software-defined radio parts of the system. It was all the way back in 2001, and it's still incredibly popular. Tons of people using it. It's very interesting. So before I get into the Python side, I got into it first with just the Linux software-defined radio applications. The first one is GQRX, an open source software-defined radio receiver powered by GNU Radio, and the Qt graphical toolkit, which I have up here. I'll have to restart it once folks are finished with the thing there. If we are. We're good. Let me get that back. I'll plug it in and actually use it, so it's not just a big piece of equipment. It actually works. Thanks. So yeah, the one piece here is a USB device, and it actually connects to I don't remember what type of connector this is. I think it's a SMA connector, and the actual antenna itself is not really clearly for a specific frequency. I'll get into some frequency-specific things later, but this is kind of just a general antenna. I found out it was actually magnetic. I don't know if that'll stay there. Just plug it into the USB, and we should be able to start GQRX. Perfect. So this is GQRX. You have the ability to specify frequencies. I've got some preloaded bookmarks in here. You probably won't be able to hear over my little speakers, but actually, I don't know if it'll even plug in and play over. Won't mess with that. So the GQRX is just a simple graphical interface to the SDR itself. So I have queued up here WTOP. If we actually look at the configuration, everything works in when you think of FM radio, you think of WTOP being 103.9 megahertz. That's 1,000,000 hertz, and I won't get into that whole mathematical calculation, but you can see there on the side there, it's what is that? 103,900,000 hertz. And so we actually get on WTOP, we hit play to actually engage the radio.
The mandate for the federal government is clear.
The SDR is actually listening
easy, but it can be a challenge for agencies, especially.
The SDR is actually listening to WTOP there. And you can see there, you can actually see that we're clearly in the dead center spectrum of WTOP. We have some other things here that kind of make it a little bit easier for us to see. So there's the sample rate size. It looks like it's doing 262,000 samples. I think that's per second. And then there's also the rate frames per second. So that's actually how quickly this is refreshing. There's some automatic things going on there. We can actually play around with some of these settings to actually make the waterfall. So the waterfall system there is just kind of showing where the signal is. I'll get into these lines here in a minute. I'll tell you now. Those are actually digital signals, and we'll talk about those next.
Did you have a problem getting it configured to work with M2?
No, I didn't really even get into that because it was actually so easy. I just was Googling software-defined radios, and for Ubuntu, it was apt install GQRX, and it worked. I plugged it in. I didn't have to mess with settings. That's why I've actually started to really love Linux even more than I did, because 5 years ago, I would have had to compile GQRX for kernel driver support. Whereas this was an apt install and it just worked. I didn't have to configure anything with the actual SDR. It figured it all out for itself. I will be 100% honest with you, it was one of the easiest things I've done on Linux, was getting this specific thing to work. It installed all the packages that it needed automatically. It was fascinating. So let's see. I guess we could see, let's see, there's actually some other frequencies out there. The other thing that I think is pretty crazy is this thing has an operating range of, I think, 27 or maybe 17 megahertz up to 1.7 gigahertz. So you can listen to a full spectrum. So we're listening to radio, your car can listen to radio. Your car, however, can't listen to, it's not very clear, but if we had a better signal, maybe if I give it some better airspace there, that's fine. We won't be able to hear it. That should technically be the Frederick Automated Weather Observation System over at the airport. And so we can actually see some other stuff going on out there. There's probably some aircraft talking overhead that we can actually hear. There might be some other signals there. But this is the signal that is constantly broadcasting from the airport, telling aircraft about the weather. So it's an automated voice system. We're down in the basement here, so we're not probably going to be able to pick it up. It is actually, I didn't actually get into it over here, but under receiver options, we can actually specify we're now in AM mode. So it's amplitude modulated, which is kind of hard, I think, to get in the basement. But if we go back to WTOP, we can actually hear it better, mostly because the signal is obviously a lot more powerful, and it's also in FM mode, which is a little easier to penetrate certain areas in a building. So we actually can pick up WTOP here. We're not going to be able to hear it, but this is the Frederick Airport. You can't really hear it, but the way the aircraft all kind of communicate, they have, at least for Frederick Airport and DC Airport, and I think Dulles, they all go through Potomac Center. So there's, in Potomac, there's a broadcast and receiving station for the FAA that's talking to all the aircraft. You can actually tune into that and listen to them if you have a very clear signal. You can hear them talking back and forth. So that's GQRX. There's other things that you can play around here with to get the signal more clear. It's pretty crazy how detailed this program can be. I'm happy to try and answer any questions anybody has, but really what I like to do is I get weird. I'll sit there and I'll just watch it because it's like a hypnotic thing, especially like when you're watching WTOP, just the way that signal's bouncing around. It's so fascinating.
Can the software filter any of that? There's some meta information that comes with the signal because my radio will display like the artist's song when the song is played.
So that's what I'm going to get into next. The question was if this system can filter any of the metadata that comes through with the signal. Now you're actually talking about the digital part of the FM broadcast, which what we're listening to right now is actually the analog version of that signal. See this line here and that line there? That's actually the HD radio section of that spectrum, which, excellent segue. It's almost like I paid you to do that. So there's an open source application called NRSC 5. This is the only application that I found that actually did the work to actually listen to that digital radio receiver signal. And so to actually listen to it, I have the command already popped up here.
These folks need some better marketing skills. NRSC 5, really?
NRSC 5? What's that?
Exactly.
Oh yeah. Well, it's some company. So the command I built this for myself already. So I had to actually build it, but it as long as I had GNU Radio installed, which was just an apt install GNU Radio. All the other components were there that I needed for this. So I was able to run through the build process and, what does it get? Remote. So I got that off of GitHub from the Ori-IO. Was the guy who wrote this. And it built fairly easily. It's installed on my system, so I can actually run the command NRSC 5. Can you guys see that back in the back there? So it's NRSC. Let me zoom in because I can't even see it. I'm right here. me a second to
I'm gonna kill that front bank of lights.
Sure. There we go. So NRSC 5, 103.9, which is the WTOP section of the spectrum, and then 0 for the actual channel that we're going to listen to, because like all computer systems like to start with 0. I don't know who decided that, but you know they're smarter than me, so we'll start with 0. And we actually listen to it. You can see that we're going through and actually picking up the different types of gain that it picks up, and then all of a sudden you can see that we've got the title WTOP News, Traffic, and Weather, artist WTOP.com, and I think
Once wrote,
There you go.
quiet people have the loudest minds. This quiet
And that's
brilliance
a-
is captured in a photograph.
that's a completely digital signal, so that's why it actually sounds more clear, at least to me. Maybe I'm crazy, but I'm pretty sure everybody else can kind of
Feel
tell,
that strength
It's
in a
clearer.
photo of the Williams system.
because that's a digital signal. It's picking up that radio spectrum, and it's a completely digital signal instead of an audio, or an analog signal.
So this NRSC file thing doesn't have any sort of graphical interface, right?
Nope,
Does it
it's-
have any-
there's-
command line?
Everything that I've seen is 100% command line for it. Yep. But what I found fascinating, I just happened to think to myself, well, that's weird that we start with 0. There's actually other signals out there on the same WTOP or 103.9 spectrum. We now also can listen to the slogan. It's it was Federal News Radio, and we're now listening to.
On this date, 50 years ago, the Civil
think
Rights
it's,
Act of 1968 became law. At the
NPR.
bill signing ceremony, President
And it's
Lyndon Johnson
the
said,
same spectrum from that WTOP spectrum, but it's on a different channel because we're looking at a digital signal instead of an analog signal. So you're able to smash more data into that section.
Is there any way to pipe the sound and I guess any extra information using this file and like any report?
So the question was if you're able to pipe the sound into another file and record it. Yeah, probably. I'm sure, especially with Linux, you're able to capture audio streams. You're able to pick this up. I didn't actually do it with Audacity, but I'm fairly confident that I can take the input sound and put it into Audacity and actually record it or do whatever I needed to there, or output it to an MP3 file of whatever sort. And then we can see that we can continue on. I think this is the last channel that they have available on this one. This looks like the WLTPFM. I just caught it there as it flew by. And we're actually now listening to some other station there. And I think the reason why it's skipping, because it's coming clear before with no skipping, it's probably skipping because of where we're at in the building. It's not picking up all the signal there, but it's there. I think that's probably what's going on with the CRC match. There's that cyclic reduction cycle mismatch. It's got the ability to make sure that you're getting the correct signal to catch itself, and where we're at in the building is obviously not the best for picking up those signals, but it's still able to broadcast it ever so slightly there, which cracks me up. And then lastly, this is my favorite. Now I will tell you straight up that this is a Java application, so don't kill me because this is a Python talk. But this is actually one of the cooler pieces of technology, well, pieces of software that I found. So SDR Trunk is a cross-platform Java application for decoding, monitoring, and recording streamed trunk radio broadcasts. So you ask yourself, well, what is that? The way that trunk radio works now, that there's large municipalities like Frederick, they have lots of people either involved in the police, fire and emergency rescue, parks and rec, portions of the government that are all talking over radio waves. And so you think to yourself, do you want to have them all on different radio waves that you have to coordinate with them, or do you pay some company to to provide you a thing called a phase 25 system, which does all of that automatically for you. So you don't have to say, hey, Joe, I'm on frequency 192 now. You have a system that's built that knows that this person wants to talk to this person, and it just coordinates all of that communication for them. And so what happens there is it has what's called a control channel. And so that control channel is a radio channel that all the radios listen to. And when they're figuring out who they need to talk to, they go to the control channel and say, I'm going to talk to this person. And that person gets told, hey, go to this channel, and then they're able to talk. That's how you essentially coordinate a large municipality. What somebody decided to write was SDR Trunk, which is a open source application to be able to, using an SDR, listen to those communications. So if we run Java jar, I have the command here. It's good. You should write them down. It's always, whenever you give a talk, write down your commands because it just makes it easier. And I actually had to compile a little bit of this. There's actually so depending on the system that the municipality uses, there's a possibility that they're actually encoding the radio traffic. So you have to build a Java library to actually be able to decode that audio. And that was fairly easy to find. If you Google SDR Trunk and you're interested in this stuff, you can figure it out if I can. It's not rocket science. But you just get all this running, and then SDR Trunk gets up and running. Now this does have a graphical user interface, and I apologize for the resolution that it's going to come in at. But so you can see here that I've already set it up to listen to Frederick. I'm not quite sure how to zoom in on it. I know it's pretty, actually it looks okay. But you can see there that it's picked up the control frequency, and you can see some other things going on, and there's some calls going on in the background that we should be able to, if I turn up the volume, hopefully somebody's talking on. We'll give it a second. If nobody's talking, then nobody's talking. But we may not have the best signal to pick up things here, but actually, it's kind of interesting. We may not pick up anything.
Do you know what the license on this is? Is it Apache or is it GNU?
I don't know. I found it on GitHub, and it was fairly easy to get up and running, so I would assume it's open source of some sort. You know what, I wonder if, no, it should be. I don't know why it's not picking up anything now, but hey, if this is the only thing out of my demo that doesn't go according to plan, I'm fine with that. Because it's Java, who gives a crap? So anyways, we'll go back to the demo here, or to the slides. So that was the different Linux SDR applications out there. They're pretty cool. If you're looking at SDRs and you want to play around with the different signals out there, you can kind of go through the signals yourself, or you can use those applications to kind of see them. There's fascinating. It's actually amazing to me how many signals are out there. You don't realize that all this stuff is going on constantly. It's just out there to listen to. And one of those things that's constantly out there to listen to is ADS-B. It's a surveillance. I stole this definition from Wikipedia again, so it's weird that it's called a surveillance technology for aircraft, but it actually is a surveillance technology in which an aircraft determines its position via satellite navigation and periodically broadcasts it, enabling it to be tracked, which you can do with an SDR. And you do so by getting a Raspberry Pi, installing PiAware on it. FlightAware will actually provide it to you. You can also go all out and buy a FlightAware dongle and a FlightAware 1070 megahertz filter. And 1070 megahertz is the frequency at which all these aircraft are broadcasting their ADS-B positions with. And now FlightAware has a couple, 100,000 people out all over the world that are weirdo nerds like me that are doing this. And they're able to pick up all these aircraft that are flying overhead. So this is actually my Raspberry Pi in my house, centered over top of my house in Frederick. And it's all of the aircraft that I'm picking up. I also have an antenna outside that's specifically built for 1090 megahertz. And I'm picking up aircraft 150 miles away because they're broadcasting this over an open spectrum. and my device is able to pick it up. And you may ask yourself, well, why would you even want to do that? Why would you want to collect these aircraft's data? Well, what you don't realize is FlightAware, because of the generosity that all the people that are collecting this for them do, is they turn around and then they sell it to Google, and that's FlightAware is actually how Google provides you the status of your airplane. So when you Google flights from BWI to Portland, that information is coming from FlightAware and other sources, but like the status of a specific flight is because of FlightAware. And you may say, okay, well, why am I providing that data to FlightAware? Well, they give you a free enterprise account, and you can look up specific things about aircraft that you're interested in. I do it because I wanted to actually find a very large data set to play around with Python. So that's actually how I tie it into this talk, is I went out and I collected helps if I get in the right location.
That's an international standard, ADS-B?
So I don't know the exact answer to that. I do know that ADS-B is currently, until next year, opt-in, or you don't currently, if you're just a regular pilot flying around some little rinky-dink aircraft, you don't currently have to, you are not required to broadcast or receive ADS-B. It's built in such a way that you kind of want to, because it will tell you where other aircraft are in relation to you. I think in 2019, or at least the end of 2018, it will be a requirement that you have to broadcast your signal with ADS-B so that everybody knows where you are as a pilot. So I started getting some of that data.
Can I make a comment?
Sure.
There's an app for that on the smartphone.
Okay.
And it shows all those planes.
Yes.
And it's very cool. But, I deleted it and I can't remember where it was.
It's probably FlightAware. So this is FlightAware here, and
Yeah,
they have all the statistics for their ADS-B receivers. They get 99 million positions an hour. Like, they're able to handle a lot of data, and it's
Putting up there and you can say that's bound for Phoenix.
The-
It's a Boeing 747 bound for Phoenix.
So you can't really see it because I'm not zoomed in on this map, but there have been numerous times where I'm looking at this at my house and I hear a plane flying overhead, and I'm able to see it fly overhead on my screen.
It tells you where it left from.
Yeah.
The destination.
Yeah. And
The
it's
type of aircraft.
my Raspberry Pi collecting that data. Like
You could see executive jets.
Yeah.
It'll say executive jet, destination unknown, or something like that.
there was a plane flying overhead a couple of weeks ago that was owned by These Pretzels Are Making Me Thirsty LLC. For those that don't know, that's a Seinfeld joke, and there's an LLC that owns an airplane called These Pretzels Are Making Me Thirsty. It cracked me up.
Can I ask you just a general question
Yeah.
about, like, are there any legal issues that you had to look into? You talked about looking at SDR Trunk and doing some encoding and, or dealing with encoded signals. Is that?
It's all publicly available on the internet. Now, I'm not saying that makes it legal, but these really what I think about is it's broadcasted radio waves. And for like SDR Trunk, you can Google Frederick County radio, and you can listen to the same signal that's broadcasted over the internet. That system, that SDR Trunk, is actually what somebody in Frederick, Maryland is using to broadcast that on the internet. They're using SDR Trunk to do that with. So in that particular case, to decode the audio, I think it's a little different because it's not encrypted radio communications, it's just encoded.
Oh, right.
Which I'm not sure, I don't know the legal mumbo jumbo behind what's the difference between an encoded signal and an encrypted signal. Truthfully, they're essentially kind of encrypted between each other, because you would really think like maybe a ROT13 find and replace could technically be considered an encryption technology, just kind of outdated and not something you would want to actually encrypt with. But so to answer your question, I don't know the legal implications. Everything that I've done so far, I'm fairly confident I'm not going to get arrested for, specifically because I'm not the first person doing it, and I haven't heard of anybody else being arrested for it. So I'm very confident that using SDR Trunk to listen to an encoded Frederick County signal is not illegal. Now, if I were trying to use SDR Trunk to listen to the encrypted Maryland State Police communications, that's a different story, which you can't do. Well, at least I don't know how to. That's a different story. Maryland State Police encrypts their radio communications, whereas Frederick County, Frederick City Police encode it. I know there's a difference. I know one's illegal, one's legal. Don't arrest me.
Encoding is probably just for a space efficiency thing. On the airwaves.
Yeah. There's that encoding probably includes some additional checks to make sure that the signal comes through properly. There's a lot of other things. It's not doing actual encryption to the communication. So this is just a repo I put together called flight parsing, and I have some data here. I called it big data because it was a lot of data. It was 604 megabytes of aircraft out there. And so I have a demo of show aircraft. So I'm using pip file, which we've kind of showed before. It's just it's the new way that requests, or not requests, that the guy who wrote requests and how the Python packages are handled now. And it creates virtual environments for you. And you use pipenv run Python show aircraft. And so that's this, and I guess I could actually open it up to look at it. I posted this on GitHub Gist, and all it's doing is taking in the data directory folder, creating some lists, and I will be completely honest, I'm not the greatest Python person on the planet, but it works, so hey, it's good enough. There's probably some optimizations that can be done, but it goes through and recursively opens all of the files, loads them in, and then actually parses it for the information we're looking for the flight reports, for the altitude reports, the speed reports, and the number of messages we're receiving, and we're going to print them all out at the end there. So if we run this, it takes a little bit, and I am running it on a smaller data set of, I think it's about 500 megs. So we saw 3,429 flights in the period of time that I had that data. The average altitude seen was 27,000 feet. The highest speed seen was 634, I think that's knots. I don't know how that converts to miles per hour, but it's super fast. The total number of messages received was, I think that's 1.2 billion messages received. So if you really think about that, that's the number of messages. And when I think in the previous slide, you could actually see the number of messages per second was around 500 messages per second that the Raspberry Pi was receiving from aircraft. So in the period of time that I pulled this data, it was about a week. In a week, it received 1.2 million messages. A little Raspberry Pi sitting in my laundry room received 1.2 billion messages from aircraft in the sky. And the number of average messages received, I actually misnamed that. It's average number of messages received per aircraft was 374,000. So that's just kind of interesting to use Python to actually take that ADS-B data and process it and kind of see what's out there. You realize like there's a lot of information that's out there. And then just to take it a little step further, I have another one that's distance.py. And actually I should probably open that one too.
What's the range of your receiver to get an idea of like how?
Next slide, right here. So distance.py is doing the same thing. It's pulling in that data, and then I'm using a package called GeoPi, and it uses some super smart math that I don't quite understand, but it calculates my location, and I obfuscated my location ever so slightly for the internet. In the actual distance.py, I have my exact GPS location. Good luck getting that data, Facebook. They already have it, so why am I worried? So I take my location, and I set up a couple of variables. I'm sure that's not actually how you're supposed to set up those variables, but when I tried to make a variable with a number on the front, Adam got mad at me, and it said that you need like a character in front, so I just put an underscore there. And then I just went through and made a very simple if statement that says if the distance created between the aircraft report and my location is less than 5 miles, put it into this bucket. If it's more than 5 miles but less than 30, and so on, put it into these different buckets. Run the same command, well, run the different command this time, but distance.py, and we will get to answer your question, which is, what is the distance that my receiver picks up? It takes a minute to run because it's doing a whole bunch of math. I am able to see positions, 295 positions outside of 200 miles away. Yeah. I think the maximum distance I've seen, which FlightAware reports, is just over 250 miles away. I'm comfortably seeing aircraft, which surprisingly, 30 to 100 miles away. If you think, well, where are all those aircraft at? They're at BWI, Dulles, and DC. Those are all within 30 to 100 miles away. So that's where we're seeing all of those aircraft. So yeah, that's one thing you can do with Python. I have a few others. I'm happy to answer any questions about this specifically. None? I think it's just fascinating that you can collect this data with a Raspberry Pi and write some simple Python to figure out, like, hey, there's all these aircraft flying overhead. One of the things I want to do, and I'm going to get with Christine about this, even though she doesn't know this, I want to take this data, because I have GPS locations over like a 30-second period. I should be able to, one thing you see with people that have done some flight parsing is they'll use the plotter to plot where the aircraft have gone on a 2D scale, but since we're so close to airports, I want to actually plot that on a 3D scale so you can actually see aircraft come in and land at a certain location. Specifically at Frederick, I'm so close and the antenna is high enough that I can actually watch aircraft taxi at Frederick Airport. So you can actually see their ADS-B receiver turn on, and they are at ground level at 0 knots in the parking lot of the aircraft, or of where the aircraft sit, whatever that's actually called. It's probably not parking lot, but that's where they park. And then they taxi out to the taxiway and go take off. And you're able to actually watch that with this receiver because we're so close to the airport there.
What does the data itself look like? Is it little bits of XML or
so
JSON?
So this this is PyWare Skyview. You can't really see it, but it's an application called Dump 1090. I didn't really want to get into it too much because it's really like a C application with some other stuff that's just pinging the receiver for information and like crunching through it at the speed of C. What it does have is a web server that presents a data JSON endpoint. So if we look at the data, and what I ended up doing was building a Python script, which I probably should have demoed here. It's a Python script that runs on the Raspberry Pi that actually pulls that data endpoint and sends it to Amazon S3, and then I just downloaded it later. But the data is split up into, I have 2 locations picking it up, one in Frederick, one in Baltimore, and it picks it up every 30 seconds, and I split it up by year, month, day, and then hour. And then the actual JSON is the Unix epoch time, or epoch time, however you pronounce that word properly. But this is the data here. It's just this JSON blob. We can pipe through JQ and actually see that it's depending on the aircraft. So not every single aircraft that comes through will actually have a location associated with it. So there's like a whole other slew of math that I didn't particularly get into, which is what's called an MLAT position fix. So it's my GPS or my Pi is getting a fix with another Pi in the area that's got another fix with another Pi, and they're coordinating all that data on FlightAware to actually provide the GPS location that's verified. And so that's where this MLAT stuff comes in. Now, the average aircraft does broadcast its GPS location. So the majority of these do have GPS locations. So it's just JSON information that has the latitude, the last time it was seen, which in most cases is fairly soon. Anything over a minute gets dropped off. The vertical rate of either ascent or descent, the number of messages received, the altitude, longitude. The hex is actually the aircraft call sign, and then MLAT information of what MLAT actually provided it. And then TISB, which is another section of information, the speed, the track, which is the direction that it's going, like what direction it's headed. And some other things like scene position and RSSI, which goes into being able to calculate its MLAT stuff. So it's just JSON. Does that answer your question?
It does.
Perfect.
Pretty cool.
Yeah. Okay, enough about aircraft. Let's get back to talking about SDRs. Python SDR library. I have a very simple demo of this. There's an open source library out there called PyRTL SDR. It's a Python wrapper for libSDR. The only requirement for this was to have, I think, GNU Radio installed, because I think GNU Radio includes the libRTL SDR. So you could also just have libRTL SDR installed on your device and it'll pick it up. But this is getting back into some very simple Python. So just to actually look at the actual thing here, we can copy. Actually, I took a screenshot of that, so that's not actually what it's going to be. But we can actually run this word for word and get the exact same response. Actually, I did include this in. I think it's.
So this works because your radio is a Realtek device?
Yes. In fact, the majority of the cheaper SDRs that are out there are all the same device.
Oh, okay.
Yeah. I think the only difference is when this one gets a lot of work on it, you can actually fry an egg on it, whereas the other ones you can't. I think that's the only difference. Don't sue me, New Electric. I was just joking. So in the talks GitHub repo, there is some sample code for software-defined radio, and we should be able to. I think it's simple read. Yeah, there we go. So simple read is from the SDR Python repo, which does just a very simple look at the actual SDR itself, which goes through and it sets a sample rate, which we kind of talked about earlier, the different sample rates. The center frequency, which I've set to 103.9, and then that E5 just appends an extra couple of millions on there. The frequency correction of points per minute, it'll do some correction of the frequency just to make it display a little bit better. And then we actually look at we'll loop through 512 samples of that. Now this isn't going to look very good at all, but this is actually reading the samples from the actual SDR. So those actually mean actual data coming through the actual SDR. We can actually do a little bit more with that by, make sure I'm in the right spot with my talk. Yeah, so I'm directing myself to actually go to where I was at, so good. We can actually, here we go. We can plot some of that. So we can actually look at plot PSD, which is using, let me get that up there better. Perfect. So this is using Matplotlib and a couple other pieces of Matplotlib to pull that same data, set the gain so it actually can read it a little bit better, pull in some samples, and then actually plot that frequency spectrum in Python. So we're going to run that. And we'll actually get to see Matplotlib do something interesting, which is run on the different screen there and actually make it look better. Here we go. So we are actually looking at 103.9 megahertz, the actual signal that came in at that exact moment when we took that snapshot. And we can actually still kind of see, that might be off ever so slightly, but we can definitely see the digital signal over on the other side and then the main analog signal there in the center.
What's the y-axis here?
It is relative power in dB. So it is at that point in time, a negative 33 dB signal, fairly loud for where we're located.
With that receiver that $25 receiver, can you only tune into one channel at a time?
Yes. Well, let me take that back. So it tunes into a spectrum, like a section. And I can show you again in GQRX, you can specify a larger spectrum or a very fine section of the spectrum. You can't tune into two separate locations. You could very easily, and I haven't tested this, but I'm fairly confident it works this way. You could have multiple, actually I know for a fact that it does with SDR Trunk. SDR Trunk allows you to set up multiple listeners, so you could have multiple SDRs listening to different trunks at the same time, all recording all of their information.
Yeah, that's accountable.
So let's get into this a little bit better. Let's take a look at,
One more question.
Yep.
Is there a limit to the number of, I don't know, what term it is in your channel, that you can record at the same time? Is there like a software limit, or is it just a hardware limit, or you said you could set up the SDR Trunk to record different sections of the spectrum at the same time?
with different SDRs. You'd have to have multiple SDRs to do that.
Oh, you mean multiple copies of the application?
No, multiple devices, hardware devices.
Oh, multiple hardware devices.
Yeah.
Oh, okay.
Because they're only able to listen to a specific spectrum. Now they can jump between, and that's what SDR Trunk is doing, is it's jumping to different spectrums and is using the phase 25 system to know when to jump to a specific frequency. And at the end of this channel's communication, it says, okay, go back to the control channel. The SDR is doing that. So it's jumping, but it's only ever listening to a single frequency at a time.
So can Linux, I could hook up like a USB hub and plug in like 10 of these things?
Oh yeah, and in fact, Mark, correct me if I'm wrong, I don't know how much SDR work you've done, but I'm sure in ham radio you guys are probably using a lot of these to do a lot of different listening with multiple SDRs, maybe. I would assume if I were a ham radio guy, I would probably have a good chunk of these just listening to different radio signals at all times, because I'm sure ham radio guys are on multiple frequencies, ever talking whenever, and you would have SDRs set up to listen to those different frequencies to be able to hear whoever's talking. That way you don't have to jump manually. That's what I would do, is I would have a bank of SDRs just listening to multiple channels. Yeah. So now we're getting into a little bit more stuff. Some of this I kind of pulled off the internet. This is going to create a GIF. Hopefully that's how you pronounce it. GIF to those who are semi-crazy. Of the same 103.9 megahertz, but it's actually going to take multiple samples of that same spectrum and print them to a graph using Matplotlib. Of course, it's going to go on the other screen there, but I'll move it over. You can actually see it here. It's now creating those samples there, and it's just creating this weird, crazy spectrum of data. And we can actually adjust the signal, and you can see it getting stronger and picking up more signals, and we can hide it, and it'll go back down to nothing, throw it back up, and it'll get more signal again. And it's just going to continue to do that and continue to graph that frequency there. That's just using Matplotlib to actually do that. By pulling in the actual frequency, center frequency again, setting a specific amount of gain, and then doing some Matplotlib stuff that I kind of understand a little bit. It's basically just setting up a display window, setting the x-axis and y-axis, and then going through continually to loop through and show the specific snapshot of the frequency at that exact moment. But it'll just continue to update that screen there. Let's see. And then lastly, we have a waterfall demo, which I pulled this completely off the internet. Waterfall, as I showed earlier, is just a visual representation of how nicely you are picking up that specific section of frequency. There's some additional things in this waterfall demo that kind of gives you the ability. There's some if-then statements here to increase the gain or decrease the gain, and gain just allows it to specifically listen to a frequency at a certain level. It's basically like turning up the volume or turning it down. There's an auto gain, which is built into the SDR. Maybe actually it might be built into the, no, it's definitely I think built into the SDR here, because there's no auto gain on the actual Python here. and then using some event keys of left and right to center on a specific frequency. So it's kind of interesting. There's no audio with this, but you will actually see I can tune in WTOP again. And I was doing this before with my mouse, so let's hope that the trackpad will actually get this. We're on 100 megahertz now. Let's go ahead and jump over to 103.9. We should be getting there. I think it's right over here. It's this slightly grayed out line, but we can turn up the gain to get a little bit better, or just turn on auto gain. And we're now listening to, that's the center there is actually 103 point, I think that's 103.1, so that's WFRED or whatever, 103.3, 103.1. This is WTOP over here. I'm not entirely sure why it's not picking up the digital frequencies there, but it might just be the way the signal is situated. There we go. Now you can see the digital lines coming in for that same frequency again. So it's interesting. I didn't realize that other frequency was so more powerful. That's pretty good. Yeah, cool.
So that's the Python equivalent of the GQRX thing that we saw?
I would definitely not say this is the Python equivalent. This is like the Python minimum viable product to GQRX.
I just meant of the actual waterfall
Yes.
portion.
This is using Matplotlib to visually display the frequency that is what's called a waterfall in the radio world.
Notice the difference between the music and the voice.
Oh yeah, definitely. So this is some sort of music, and this is voice. That's definitely a very interesting site there.
What's the little line over the
So I hadn't talked about that, but I'm glad you brought that up. What I've noticed that this actually ends up being, if you really start looking into it, it's actually, there's a lot of different resonance frequencies that you'll occasionally pick up. They're not actually broadcast signals. They are what are, the device is just picking up a specific frequency that is just inherent in the device. You can listen to it. It's like a tone. What's that?
Internal intermod or something like that. It's this spurious things that are generated internally because maybe one strong signal versus building and heterodyning with something else inside it.
Right. And so it's creating this resonance that it's really weird to listen to, because when you first hear it, you're like, wow, this is amazing. What the heck is this? Because it's super strong. It's like in the same room as you, like something's broadcasting in the same room. No, it's just I don't know if it's a flaw in the hardware. It's just something that is inherently there because it's a piece of equipment, a piece of radio equipment that just has other things happening that are just, they kind of meet at the same point. And it's here in this one, and I can pull it up on GQRX. You can find, like every couple of thousand or every couple of hundred megahertz, you'll see resonance frequency pop up. It's just weird. At first you see it and you listen to it and you're like, what the heck is this? This is really strange, but it's just when you start looking into it, it's called a resonance frequency. I don't know much more than that, other than it's just inherently with the equipment. Anybody know? Okay, great. And then finally, and I'll be done talking, I promise. Lastly, we have another thing that I stole off the internet, using Python to make an FM radio. This was super cool. This was all out on the internet. The virtual env works, or all the instructions on the actual RTL FM Python all work. It's all in Flask. The build command just makes sure that you have the libraries installed that you need, and then you just start the web server. I'm happy to show the actual the Python behind it, but it's really just a Flask application that is a more detailed version of the waterfall, but instead of showing the waterfall, it's showing the FM, or making the actual audio come through. So what we have is we can...
So you're saying this is a web server that you're picking up a somewhere and broadcasting it over the web. Is that it?
No, it's picking up the radio station. Give me 1 second to get to it.
Browser radio.
Yes, so what it's doing is it's starting a Flask web server that you navigate to locally on your system, and you tune in the radio signal, and the radio signal comes through the speakers.
Oh.
So there it's starting the actual application up, and we see up there above it says to go to this location here, copy that address. I haven't tested it internally here, so we'll see if it actually works. So it's currently tuned into 101.1, the greatest radio station of all time. We can change the modulation to FM. I don't know why it defaulted to the other one, but let's go ahead and pick up 103.9, which is going to be a little stronger down here, I think.
So you're not streaming the audio over the network. You're just using that web server.
Correct. It is 100% locally to this system, and it should hopefully play the audio. You have to play with it a little bit to get it to pick it up, and it may not work at all. I think it's working. Perfect.
And begin to demand to be compensated for it. It's really the
There you go. And so it's a Python app running in the browser, playing that radio signal.
Seems like wouldn't be too difficult to modify that so you could stream the audio.
Oh, definitely.
Yeah.
I'm confident that you can do whatever you want, especially on Linux, because it's the best. I think that's it. Yeah, that was it. I didn't put a question slide in, but questions, yes.
Is the hardware itself it's hard for me to call it the software-defined radio. The hardware piece itself, is it doing something in hardware beyond just receiving the radio? Like, is it doing sampling in the hardware?
I don't know for a fact the answer, but what I assume is happening, because when you look at, let me kill this and open up GQRX, because this will hopefully, I think, answer your question. So GQRX specifically has, you see this section here, the grayed out portion there, that actually changes when you specify the mode. So if we change it to AM, it gets super tiny because AM only cares about the modulation between the signal, like the up and down motion, whereas FM is completely dependent upon the modulation of the signal going this way. And so for this, there's a very key point. This center line here is actually what the tuner, what the actual SDR is currently tuned to, is that center frequency. And then the software, so you see the hardware frequency is 104.153 megahertz. We can hit play, and we're listening to WTOP currently, which it's not coming in very clear, but we're centered on 104.1, but it's listening to 103.9. So what it's actually doing is that center frequency, the hardware is tuned to 104.153 megahertz. The software is shifting it to 103.9. See what I'm saying? So I think that answers your question. I don't know the actual...
The center of the spread.
Correct.
But then you specify with software what you're actually doing.
Exactly. I think...
So that's the range.
I believe that answers your question. Maybe not.
I guess I have a follow-up question.
Okay, sure.
And not for various purposes, but
Yeah.
I'm thinking about why you couldn't use one of the other hardware interfaces on your machine to receive radio signals like Wi-Fi. I mean, it's radio, right? I mean, I know that we limit it to, perhaps we limit it to certain range of frequencies. I'm just thinking about, I mean, for my purposes, I
So just for the NSA that's listening, the guy in the glasses with the beard wants to use his Wi-Fi card to listen to other signals. Just so I'm just joking. I think I suspect where you're going with that. The reason that we're limited to, at least with GQRX, is it's all library based. So the SDR is providing a USB interface to its hardware, and that is being picked up, at least on my Ubuntu system, via libSDR. And so there's C packages and just general, probably assembly of some sort, who knows, information that was written to communicate with this device. Maybe, I have no clue how to actually answer the question, but I would assume to be able to do that, there would have to be a common platform that another radio device would have to be able to publish to the system, and then libraries would have to be written to listen to that to be able to do the same thing that's going on here. This works from 17 megahertz to 1.7 gigahertz, so it's just under that 2.4 gigahertz to be able to listen to Wi-Fi. But there are definitely SDRs out there that even go higher than 1.7 gigahertz. You're going to have to pay more than $25 for them, but they definitely exist. Mark was talking about there is, so the lower limit of this is 17 megahertz. There are up converters that exist that allow you to listen to below 17 megahertz, but what it does is it actually converts it into a frequency on here that shows up as 500 megahertz. But you just have to know the switch in your head that even though I'm looking at 500 megahertz, it's actually 2 megahertz because I'm going through this hardware filter to be able to up convert that signal.
I don't think you would need one of these devices to snip all the packets, all the Wi-Fi packets going around. You can do that on Linux. Right?
Correct.
With a regular.
Right, with Wireshark, you can definitely do that.
It's
Yep.
just, you wouldn't be able to connect, but you could, because it's encrypted.
Right.
But you could set all that up.
Correct.
You
Yeah,
and
already
some
got
of that,
that.
some of somebody's house.
Yep.
Yeah, so as a comparison, the other radio I was talking about does from 1 megahertz to 6 gigahertz.
Interesting. And that's
Significantly more money.
100, like, what is it, 100 some odd dollars or
It was like 300.
300? Yeah. I mean, to be able to listen to, with this you get to listen to FM, AM, aircraft. I didn't get it to work just right. A buddy of mine and I tried to actually listen to the NOAA satellites that fly overhead. If anybody's seen the movie Contact, there's the favorite quote of mine where she disappears, but they say, oh, she wasn't gone because she just went right through the system. Well, then they say, well, why did she have 18 hours of static? When we listened to the satellite, we had a static image. It was all static, but it was correctly formatted to the width that would have been broadcasted. So we did receive something. We just got a lot of static, so it kind of sucked. But the idea of being able, you can actually listen to satellites that are constantly flying overhead and get their weather data. They broadcast publicly the actual images from the satellite as they fly overhead taking pictures of clouds and atmospheric conditions. You can pick that up. That's what the weather channels of the world are actually using to provide that as their thing. They're pulling that data down and then they're doing additional things on it to figure out when it's going to snow next.
Should we turn this on during thunderstorm or something?
Bam!
Probably, yeah. It's, who knows?
I guess it's, I don't know, thunderstorms, is it all random frequencies, all random radio frequencies it generates? Is it some?
Anybody got some static electricity? We could just hit it right now.
I was reading a line, depending on the frequency, you can listen to meteor showers.
Oh, wow.
Huh.
It is, I mean, some of them go down into the kilohertz range, and they say it's fascinating. You can hear the Perseids coming through. And it's very interesting.
Well, hey, that's, I hope the talk was good. I know there wasn't too much Python, but I did get some Python in there.
Yeah, that's great, thank you.
Cool. Hey, great. Thanks. Appreciate you coming out.